In this chapter, we've examined the relationship between our rectangular coordinates, x, y, and our polar coordinates, r and theta. But now that we've started to talk about complex numbers, what relationship is there between complex numbers and the polar coordinates? So here we have the complex plane, and we have some complex number z plotted in the complex plane. We want to know, how can we express z in terms of the polar coordinates? This distance here, this blue, we call that the magnitude of z, is just the square root of x squared plus y squared. If you recall, in polar coordinates, this distance was just r. It was called r. So we can talk about the magnitude of z being r, so that's a relationship that it shares with polar coordinates. But we also know that x in polar coordinates was just r times the cosine of theta, and we know that y was just r times the sine of theta. So if I want to take this complex number and express it in polar coordinates, I can use this fact and substitute in r cosine theta and r sine theta for x and y to then express my complex number as a polar coordinate, or in polar coordinates. So we have z equals, x is just r cosine theta, plus y, which is r sine of theta, all of that times I. Now we can kind of clean this up a little bit and make it a little neater. And to do that, we're going to factor out a r. So we'll have z equals r times cosine of theta plus, and to make it less confusing so that it's clearer that I is not part of the argument of our sine, we'll pull the I out in front. So it's z equals r times the quantity cosine of theta plus I sine of theta. And this is how you express a complex number in polar coordinates. So for this example, we want to write an expression for z equals 2 plus 2i. So this is a complex number, and we want to write it in polar form. We want to express our argument in degrees. So the value of theta we want to express in degrees. So first, it recommends that we plot z to determine what quadrant our angle should be in. So let's go ahead and plot z. So this is remember, this is the real component, and then this is the imaginary component. So on our coordinate plane, we have a real component of 2. So we go out 1, 2, and then we have an imaginary component of a positive 2, 1, 2. So this point here is 2 plus 2i. So first, it asks us to find r. So if you remember, we said that r was just equal to the magnitude of z, and that was found by taking the square root of x squared plus y squared. So that's this distance here, right? The distance from the origin to our point. So this is going to be equal to the square root of 2 squared plus 2 squared, which is the square root of 4 and 4, which is 8. And then this will simplify to be 2 rad 2. So this is the value of r. And now we need to find theta. Well, if we were to construct a right triangle here, we would have that we actually don't even need to do that. We can just say that we know that the tangent of theta is equal to y divided by x. So y is 2 and x is 2. So this gives us the tangent of theta equals 2 divided by 2. The tangent of theta is 1. So we want to know what value of theta gives us a tangent of 1. And again, remember, we're looking for an angle in quadrant 1. So we're talking about angle quadrant 1, whose tangent is theta. That's going to happen at pi over 4 or 45 degrees. So in this case, theta is 45 degrees. So if we want to write this complex number in polar form, it's going to be, what is it going to look like? Z equals r, which is 2 rad 2, times the quantity, the cosine of theta, which is 45 degrees, plus I times the sine of theta, which is 45 degrees. And again, we're expressing it in degrees because that's what the direction said to do. So our polar coordinate, our polar form of the complex number is 2 rad 2 times cosine of 45 degrees plus I times the sine of 45 degrees.